Hey guys, my name is Shreyas and welcome to Simple Chemistry. In the previous video we talked about electron configurations. We started to get this idea of how atoms configure their electrons within their orbitals. Now you might be a little bit confused on still how exactly it's working. So today we're going to really show how these electrons are being distributed by drawing electron distributions. And I think you're going to get a better understanding of how the electrons are really being placed in the atom, as well as those three rules we talked about here, the off-by principle, the Pauli exclusion principle, and Hund's rule, and how everything really ties in together. So let's get right into it. Okay, here. So let's go ahead and write the electron configurations for these three elements here. I mean the electron distribution. So we know that nitrogen is all the way up to helium, and then 2s2, 2p3. So let's go ahead and look at what an electron distribution is. So basically what an electron distribution is it's a better idea of how the electrons are being distributed. So let's see, nitrogen was, if you look back, it was helium, which is 1s2, 2s2, and then 2p3. Yeah. Okay, so the first thing you need to do is look at the electron configuration. This is called the electron configuration. Okay. Now we need to actually look at the electron distribution, which is what we're going to do. So what we do is we start drawing like these lines to represent our orbitals. So we start with the 1s orbital here, and then the 2s orbital, and then in 2p there are 3 orbitals, right? There's 2p x, 2py, and 2pz, so we stop there, okay? And now we can start distributing the electrons, okay? So the way we do this is, if you look back at these rules here, the off-by principle says electrons enter the lowest energy levels first. So what that means is that this is increasing energy like this. So the 1s orbital has not as much energy as the 2s orbital, which has not as much energy as the 2p orbitals. These 2p orbitals are all said to be degenerate. We talked about how electrons, how orbitals can sometimes have the same energy. So all these 2p orbitals have the same energy. They just have different orientations. So same energy, different orientations. So basically, the orbitals are degenerate in any atom whenever they have the same orientation. So you can think of it as the orbitals in any sublevel are degenerate. Okay. Again, the orbitals in any sublevel are degenerate. Okay. So there's that. So that means we can't start putting our electrons in the 2p. We have to start at the very beginning. So we know that there's that. And another rule we need to follow is Pauli exclusion principle, saying an electron must have at most 2 electrons, and these electrons must have opposite spins, which we'll indicate. And then Hund's rule says every orbital gets an electron before an orbital gets 2, which we'll see here. So what we simply do is each of these represents an orbital. So we start here. Since 1s2, there's 2 electrons, so we can just put 1 like this, meaning that this has a 1 spin, and then there's another one here which means it has the opposite spin. This arrow indicates maybe like a clockwise spin, while the other one indicates a counterclockwise spin. That's Hund's rule. And then 2s, you have a spin and another one. So this is clockwise and counterclockwise. So 2 electrons there. And then 2p3 within that sublevel. Remember, these are showing sublevels. So within this sublevel, we have 3 electrons, but we have 3 orbitals. Okay. So what are we going to do here? that's when Hund's rule comes into play. It says every orbital gets an electron before an orbital gets two. So that means we can't put both electrons here. So we're going to have to put one electron here, and then one electron here, and then one electron here. Okay? We can't just fill it up we can't just fill up the orbitals, like we can't put two here and one here. We have to put one in each before we start to put the second one, okay? So what this basically is saying is that we have, let's look at an atom. Let me actually draw this out. So the atom here. So we have the 1s orbital, which kind of will look like a sphere. And that has two electrons. Then we have a 2s orbital, which is a little bit bigger, and it has two electrons. And then we have three 2p orbitals. So we have a p orbital here, p's of x, p's of y, p's of z. So we have the 1s orbital with two electrons, the 2s orbital with two electrons, and then each of these p orbitals with one electron. And they're all traveling within these regions of space like this, okay? So now I think you should get a better understanding of how the electrons are being distributed. Let's go ahead and do a couple more so you can get some practice. So let's go ahead and do it for gallium's a little far. Let's see. Okay, I guess we can do gallium. Okay, so if you look back, the first things we need to do is write the electron configuration for gallium before we even start. So if you look back, that was let me see, 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. Okay, can you just write that down? 1s2, 2s2, 2p6. And then 3s2, 3p6, 4s2. Then we had 4s2, then we get back to 3d10, and then 4p1. Okay, so from here we can draw all of our orbitals, okay? So we know that at first there's the 1s orbital, and then there is the 2s orbital. There's only one orbital within each sublevel. Remember back from the previous video we talked about an s sublevel has one orbital, a p sublevel has three orbitals, and a d sublevel has 5, and the f sublevel has 7. Okay, so that's why we're only drawing one orbital. But now we know p sublevels have have 3 orbitals. So 1, 2, 3, and then we indicate all of them with 2p. So this is one 2p orbital. It's another 2p orbital. It's another 2p orbital. Then 3s, we will know that the s sublevel only has one orbital, and then 3p6, which is 1, 2, 3, and then 4s, and then 3d10. Now here remember that a d sublevel has 5 orbitals, so we're going to have to draw 5 of them. So 1, 2, 3, 4, 5, and then finally 4p1. So we know in the 4p sublevel we have 1, 2, 3 orbitals. Okay? So now that we have our orbitals figured out, we can go ahead and distribute our electrons. So the 1s2 indicating there's 2 electrons, so we know that's within this orbital there's one with one spin and one with the other. Clockwise, counterclockwise. Here also clockwise, counterclockwise. 2p6. Now we have 3 orbitals, so what we can do is, even though you might say, okay, we can just put clockwise, counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise. It's good practice to use Hund's rule. So every orbital gets filled up first, so you can write it like this, before the every orbital gets one electron first before one starts to get 2. So 1, 2, 3, and then 4, 5, 6. Okay, 3s2, so that's clockwise, counterclockwise, and then 3p6, every orbital gets 1 electron, so 1, 2, 3, before each orbital gets 2, so 4, 5, 6, 4s2, so that's just clockwise, counterclockwise, 3d10 again. So every orbital gets one electron. So 1, 2, 3, 4, 5, and then before each one gets 2, so 6, 7, 8, 9, 10, and then 4p1 we just have one electron here. Okay. So this is electron distribution, and if you're looking at the atom here, let me go ahead and put this in a molecular perspective. I mean an atomic perspective. So we have the nucleus here, and then we have a 1s orbital, okay, with 2 electrons. This 1s orbital has 2 electrons. Then we have a 2s orbital, which has 2 electrons. Then we have 3 2p orbitals. So that would be 1, 2, 3. And each of those orbitals have 2 electrons. And then we have 3s orbital, like that maybe, which has 2 electrons. And then we have 3p orbitals, so that'd be even bigger. Let me use a different color. So 1, 2, 3. Each of those orbitals have 2 electrons. Then we have a 4s orbital, which is even bigger. And then we have a 3d orbitals, and that's when we get the interesting shapes, like 1. And then, it just keeps building on top of top until it turns into this really complex mix. Obviously, it just starts to look like just a bunch of gibberish. But as you can see, like, I think you can imagine it now, like how all the orbitals are coming together and lying on top of each other to form this very, very complex electronic structure, okay? I guess we can do one more problem. You know what, let's just go ahead and do this. Gold, even though it's such a long electron configuration, I guess if we can do this, then it's going to can ensure that we understand how to do this. So, gold, it's all the way up to xenon. Oh my goodness. So, I think I wrote it down here. Yeah, this is it. Let me see if there's a way of copying. Okay, so that. And then let me complete it. So 6s2, and then I think it's 6s2, 4f14, 4d9, right? 4f14, 5d9, sorry. 4f14, 5d9. So this is electron configuration. Now let's go ahead and write the electron distributions. So what we're going to have to do is, first, again, indicate our orbitals. So we know in the 1s sublevel, we're going to have a 1s, just one s orbital. In the 2s sublevel, we're going to have just an s orbital. The 2p sublevel, we're going to have 3p orbitals. So 2p, 2p, 2p. And then 3s sublevel, we're going to have just one s orbital. And then in the 3p sublevel, we're going to have 3p orbitals. 3, 1, 2, 3. In the 4s sublevel, we're going to just have one s orbital. And then we go to 3d. 3d sublevel, we're going to have 5d orbitals. So 1, 2, 3, 4, 5. And then in the 4p sublevel, we're going to have 3p orbitals. So 4p, 4p, and then 4p. And then 5s sublevel, we have just one s orbital, so 5s. 4d sublevel, we're going to have 5d orbitals, so 4d, 4d, 1, 2, 3, 4, 5. Wow, this is going to be very long. And then 5p, let me get another tab going. Oh my goodness. So we're at 4d, and then we need our 5p orbital, so we can just put, let me see here. So 5p1, 2, 3, and then 5p6s, which is just one s orbital, and then 4f14. Oh my goodness. So 1, 2, 3, 4, 5, 6, 7. Okay, because there's 7 f orbitals, and then finally we have the 5d9. So there's 1, 2, 3, 4, 5. Okay, so even though I think here I drew all 3, I drew. Let me see if I did that. Oh, this is important. I don't know why I didn't do this here. Like, I know in this example, I drew all 2p orbitals. Here, you should probably do that, dude. That's good practice. Even though that we have only 1 electron, make sure you put 4p and 4p here. So indicating that we have empty orbitals within that sublevel. Because I know my teacher actually preferred that we did this. Don't just put just 1 4p. Make sure you put all 3. Just like that. Here, make sure you put all the d orbitals within that sublevel, even though they even though not all of them are filled, right? And then we can start filling them in. Let's quickly do this. This video is going to start to get long. So 2 electrons here, 1, 2, and then 1, 2, 2p6. So 1, 2, 3. This is Hund's rule. 4, 5, 6. And then 1, 2, 3p6, 1, 2, 3. Again, Hund's rule. 4, 5, 6. 4s, so 1, 2. 3d10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 4p6, again, 100, 1, 2, 3, 4, 5, 6, and then 5s, 1, 2, 40, 10, 10 electrons, 1, 2, 3, 4, 5, 100, 6, 7, 8, 9, 10. 5p, so that's 1. Oh my god. 2, 3, go back. 4, 5, 6, and then you can look back at 6s2, so 1, 2, and then 4f14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then I think it was 5d9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and you stop there. Okay, and then another thing I want you to take from this is remember that as you increase as you increase in these orbitals, it's increasing in energy. So from here, let's say there's a question that said within gold, which orbital has more energy? One of the 4D orbitals or the 3D orbitals. So we can obviously see that since this comes later on, this is going to have more energy. And that's because of Aufbau's principle. Aufbau's principle says that the electrons are being placed in the lowest energy orbitals first before they are placed in higher energy orbitals. Okay. Another thing I want you to take is the degenerate orbitals. So these 3 would be degenerate because they're all in the same sublevel. These 3 would be degenerate because they're all in the same sublevel. These 5 would be degenerate because they're all in the same sublevel, as well as these 3, and then these 5, and then these 3. They're all in the same sublevel, all degenerate. And then these 7 are all degenerate because they're all in the same sublevel, and as well as these. Okay. Now let me see what else I have here. This video is getting very long. You know what? Actually, let me just cut this off here, and then I guess we can do a third video because this is starting to get long, and I want to keep these videos, under 20 minutes. So, in the next video, we'll talk about ion electron configurations and ground state versus excited state. But for now, just make sure you study this. Electron distributions are as simple as that.